Welcome to my presentation. This is Huajie Chen from Alibaba Group. I'm going to present HeteRSGD, tackling heterogeneous sampling costs via optimal reweighted SGD. This is joint work with Ziyang and Jianfeng from Duke University, and also my colleagues Xingshan and Wu Tao. Throughout this talk, we'll focus on the following general finite-sum optimization problem, which arises in many application domains, most notably in machine learning. But unlike the typical setting, here we are interested in a case where the evaluation of each function fi or its gradient can incur a considerable cost. So here the cost can mean things like time or computing resources or anything it takes to evaluate the function fi or its gradient. And in these cases, when you run an optimization algorithm, the sampling cost of the algorithm is of primary concern. And more importantly, we consider the heterogeneous case, meaning that the evaluation cost of different components fi can be substantially different. This is often overlooked in the current literature. And such scenario appear in applications such as algorithm auto-configuration. Let's say we may want to tune the parameters of an algorithm on a set of instances. So among these instances, some can be easy to solve, some might be hard to. Therefore, evaluating the algorithm on different instances can lead to very different computation costs. Okay. And some other examples include multi-stage stochastic programming, where the evaluation of fi may involve solving subproblems of different complexities. And also in federated learning, we may have heterogeneous clients with different processing capabilities and data size. In these problems, one popular method is, for example, stochastic gradient descent. And our goal here is to exploit the heterogeneity of the problem to accelerate these algorithms so that this algorithm can give us a good solution with lower sampling cost. So before diving into our approach, we'll first introduce our cost model for the problem. For each component I and arbitrary solution x, the cost of evaluating the gradients of fi and x is a random variable ci hat. And second, when we do multiple evaluation of the gradient, we assume that the cost of each evaluation is iid. If we run an algorithm, the total cost of the algorithm is cumulative, meaning that the total cost takes the form of the summation of the cost of each single evaluation. So here's the main idea for exploiting heterogeneity. We will start from the standard SGD. In standard SGD, we randomly sample a batch of functions uniformly from all the components. And for convenience, let's say this sampling is done with replacement. Okay. Then we form the gradient estimate by averaging all the sampled gradients, and then update the solution with a certain step size. If we look at the average sampling cost per iteration for the standard SGD, it's in this form, which is the average cost of all the components multiplied by the batch size. So we see that this cost is solely determined by the problem, and it can be high if a fair amount of the gradients are costly to evaluate. Okay. So our goal here is to reduce the sampling cost using importance sampling. So importance sampling is a technique from Monte Carlo computation that samples from a different distribution than the original one. So in here, instead of doing uniform sampling, we sample each component with non-uniform weights, P1, P2, up to Pn. But now each gradient has to be rescaled by a factor that depends on the weights. This reweighting factor is used to correct the bias so that the resulting gradient estimate is still unbiased. Now we can use these weights to control the frequency at which each component is sampled. Okay. So the key idea is really that we want to choose the P so that the costly functions are sampled less frequently so that the average cost is lower. So based on this kind of idea, a straightforward intuition is that the optimal choice is to put all the weights on the cheapest function. So here is a very simple example to illustrate that such kind of intuition is wrong. We'll consider an example with two components, and the sampling cost for the components are 1 and 50 respectively. So the second component is more expensive. So according to our previous intuition, we should use a large value for P so that the second component is sampled less frequently. So now we plot the error of the solution with respect to the total sampling cost. And we see that as P increases, the performance first improves, but when P is too large, the performance is no better than standard SGD or even worse. So the reason is that if we look at the variance of the gradient estimate is in this form, and we see that if P is close to 1, this variance will blow up. So in fact, the best weight in theory suggested by our algorithm is 0.87. So we see that the key challenge here is to choose the weight to balance the sampling cost and also the gradient variance. So here's how we choose the sampling weights. Suppose we are currently at the solution xk and want to choose a good set of sampling weights, PIs. Okay. So for every possible sampling weight PI, we'll define its sampling efficiency metric in this form. And next, we will choose the minimizer of this metric as our final sampling weights. So to understand this metric, I put down the formula for the gradient estimate. And if you calculate the variance of this gradient estimate, it will be in this form. Okay? And the first term is simply the expected cost of a single gradient evaluation if you sample according to P. And by minimizing this metric, we can obtain a sampling weight that induces both low cost and low variance. So for now, this choice of the metric may seem heuristic, but we'll show later that this actually is the optimal way. So one potential issue with this metric is that it is non-convex in the weights PIs. However, we show that by analyzing the Lagrangian, we see that the optimal weight PI star can be in this form. Okay. So in order to solve for these optimal weights, we simply need to choose the kappa star value here so that all the PI values sum up to 1. And this can be done by bisection. I also want to mention that our use of important sampling is very different from its traditional use. For example, in Monte Carlo computation, it's used to estimate quantities that is otherwise very hard to estimate. And in SGD, it's used to reduce the variance in gradient estimation of a preconditioning of the problem. Whereas in our case, we use important sampling to control the frequency at which each component is sampled so as to lower the sampling cost. So in order to use this metric in practice, we see that this involves several unknown quantities. So we'll replace all these unknown quantities with their empirical estimate. In particular, the CI tilde will be the average cost per sample from the ith component so far. And for the individual gradient, we'll estimate by the most recently sampled gradient from the ith component. And for the overall gradient, we use the average of all sampled gradient to approximate. Okay. So putting together all the elements, we have our HeteRSGD algorithm. Okay. So this algorithm may look very detailed, but the only difference of this algorithm from the standard SGD is that now the components are sampled according to a carefully chosen sampling weights, PK here. And this PK comes in 2 steps. The first is that we minimize the empirical efficiency metric from the previous slide to obtain this P tilde K. And then we further mix this sampling weight with the uniform weight. So this step is to introduce some regularization effect so that the resulting sampling weight PK will be guaranteed to be bounded away from 0. And one thing to note is that we'll typically choose this WK to converge to 0 eventually, so that eventually our sampling weights will not be affected by this mixing step. So here we provide our asymptotic convergence theories for general SGD schemes with important sampling. So please note that this is for general IS-based SGD algorithms, so that we can compare different variants later in this framework. And a few notations. So our result will be for the average solution, including Pollyak-Rupert and alpha suffix averaging. And our theory shows that for strongly convex and a smooth case, if the sampling weight pk finally converges to a limit p star, and also under some condition on the mixing weight, we show the following central limit theorems. So I want you to pay special attention to the middle one, which states that the gradient of the objective at the average solution and rescaled by the square root of the total sampling cost converges to a normal distribution. And this normal distribution has mean 0, and the variance is C times G that depends on the limit P star. Okay. So this type of result is different from previous CLT in the literature because now this gradient error is rescaled by the square root of the total sampling cost rather than the number of iterations. Okay. And such kind of new CLT result allows us to measure how fast the algorithm converge with respect to the total sampling cost. So we'll use this variance to compare different SGD variants. To do so, let's see what this covariance is. If we take a trace operator on the G function, then this left-hand side effectively measures the L2 norm of the gradient error. We can show that this error is equal to this formula on the right-hand side in red. And so if you look at this red part closely, you will see that it matches our previous sampling efficiency metric. And remember that our method works by minimizing this metric to find the sampling weights. Therefore, our method effectively minimizes the asymptotic error in this central limit theorem. Okay. So therefore, our HeteRSGD will produce the optimal sampling weight asymptotically, and other SGD variants will produce suboptimal weights. For example, the standard SGD and also SRG, which is another SGD variant that uses important sampling, but only considers gradient variance. So here we provide some experimental results. We first show you some results on synthetic data. So here we set some of the sampling cost to be epsilon squared and some to be equal to 1. So in this case, if we use a small epsilon, the heterogeneity level will increase. Okay. So here's our result for different values of epsilon. And here we plot the solution error in relation to the total sampling cost in each case. And you can see that as epsilon value decreases from 1 to 0.01, the advantage of our algorithms compared to existing SGD variants becomes more and more significant. And this summarized our result on some real data. The first two plots shows the result for logistic regression problem on 2 data sets. In the last plot, we try our method on a non-convex problem. Although our theory is for convex case, we show that empirically our method also have the same advantage as in the convex case if we apply the method to a non-convex problem. To summarize the talk, we bring up sampling cost heterogeneity that is common in optimization applications, and a novel use of important sampling that directly save cost by controlling the frequency of different components, and also at the same time control the gradient variance. Okay. And we present asymptotic and finite optimality theories of the algorithms, and also show some promising empirical results. Thank you.